Welcome to a Simulation Expert's Guide to Formally Proving Software Status and Interrupts. My name is Neil Johnson. This presentation starts with a quick comparison of simulation versus formal. I am, as the title suggests, I'm more of a simulation guy. And I am new to formal property checking, so I'll pass on a few of the things that I have learned along the way, and just a comparison of the two approaches. So both simulation and formal are used to verify functional correctness. I see this as being the same between the two technologies. How they do that is obviously different. Simulation uses simulated tests. Formal property checking uses properties. Different method for the same outcome. Tools are obviously different. One is using a simulator and the other one is using a formal engine. And then looking at the closure metrics here, these are also very similar. So in simulation, I'm used to looking at test status, so looking at passing test status from a regression. I'm looking at code coverage from a regression. I'm looking at functional coverage from a regression. And with formal property checking, a lot of that is the same. You're looking at proof status instead of test status. You're looking at code coverage. You're also looking at functional coverage. So while the technology is different, really the method and the means and the outcome between simulation and formal property checking have a lot of similarities. Looking at some of the advantages and the disadvantages between simulation and formal property checking. Again, me being more familiar with simulation, a significant upside here is that simulation, not just for me but for a lot of verification engineers, is known technology. It's kind of our default mode of operation and verification. Downside, well, let's stick with the upsides. Upside of formal property checking, I think relatively speaking, there's a low infrastructure requirement. You get proofs that are exhaustive, so you're exhaustively proving outcomes, and you have what I'm looking at as calling implicit code coverage. So formal tools give you the opportunity to explore configuration space. For me, it's more convenient than simulation. So in simulation, you have to reconfigure or run tests multiple times with different configurations and aggregate coverage across those different test runs. With formal, a lot of the times you can cover different configurations within the same proof. So again, it's just more convenient there. So moving to downsides, on simulation, again, sticking with that coverage closure aspect. In simulation, you're doing this iteratively, so you may run the same test multiple times to close coverage. You're looking at constrained random unknowns, so there is a lot of uncertainty in simulation when you've got a lot of a highly randomizable test bench. Sometimes debug can be pretty challenging because you don't know necessarily where the test is going. And a big pet peeve of mine, there is a high infrastructure requirement. This is specific to UVM, but I think it can be generalized across simulation. As verification engineers, we build a lot of infrastructure as part of a test bench. Now, the downside of formal property checking, I think ramp up and learning curve is something that verification engineers, if you're not familiar with firsthand, you're maybe scared of that ramp up or learning curve if you're coming too formal from simulation. There are technology limitations, I think, with formal that I think, again, everybody is relatively familiar with. But I think one significant barrier here is we don't necessarily know how or where to apply formal property checking. So this for me was a really big hurdle in that I didn't understand where to apply it or what type of circuit to apply it to. And then last of all, we'll look at motivation. So again, as a verification engineer who is used to doing simulation and has been doing simulation for many, many, many years, and I don't think that I'm alone there. Simulation is has been and still is and will continue to be kind of the major workhorse in verification. And that makes it default technology. So a lot of us, I don't think we think about the technology before we apply it. I think we know simulation and therefore we use simulation. Not necessarily a great motivation, but it is what it is. And just to give you a feel for, I think, how deeply rooted simulation is relative to formal in verification. So I did a quick keyword search. It's included in the paper, comparing not simulation in general, but even just UVM and the focus and attention that UVM has got in thought leadership and verification, specifically from DVCon, but I think this would apply to other conferences as well. You know, UVM has received a lot of attention by the verification community in general, specifically relative to formal. So I think you could probably multiply, you know, the orange line relative to the blue line there. You could probably multiply that orange line by a reasonably big number, and I think that it represents our the attention we give simulation relative to formal. Now, my motivation for using formal, I think there are a couple legitimate motivations. One is increased confidence, and that comes from the idea of having exhaustive proofs applied to your RTL. For me, that is secondary. The primary motivation for me is to eliminate simulation cycles. So take the constrained random sim cycles that are you know, not necessarily productive or constructive, and eliminating as many of those as we can with the addition of formal proofs and formal property checking. And that leads us to the purpose of this paper. I want to eliminate because as the primary motivation for using simulation. Just because we know it doesn't mean that we should be using it in all cases the way we do. My motivation there is to be able to eliminate some of those sim cycles with a technology that is more productive. But how do we do that? I'll give you a feel for where I have gone with formal property checking to get my feet wet. One is module level proofs. This is something I won't necessarily talk about in the paper, but it is something that I have done, and I think that it is something that maybe presents an obvious starting point. But we will talk about today is formal property checking applied to software status and interrupt checking. And this, I think, is I found it to be a very reasonable application and a very good starting point for formal property checking, specifically for folks that are coming at it from a simulation background. And ultimately, you know, in terms of looking at it as application of formal property checking, I hope that this and others can be the start of a trend where simulation engineers, or verification engineers that are used to simulation, take a real serious look at applications that are applicable to formal and make a serious attempt at realizing those applications with formal. Which takes us to really the introduction to the topic. And so we'll talk about checking software and status interrupts with formal property checking. And I think the reason why I've gone down this path is that as I have done this in simulation, I realized that really any kind of checking or interactions on the software interface tends to sometimes be very minimal. We give preference to architecting, you know, again, architecting large UVM test benches, but around core data path functionality and status and or software interactions tend to be more of an afterthought or an overlay to the test bench. So they don't focus. That's not the primary purpose of the test bench. The primary purpose is testing main data path, and then afterward we do what we can to verify the software interface and software interactions. I've seen that formal property checking gives us a better chance, I think, of reliably verifying the software interface. So it enables a more deliberate approach. So it's focused specifically on the software interface, not necessarily on the main data path that you would use simulation to verify. This focuses specifically on the software interface, and it gives you a means for dedicated checking without a lot of the infrastructure dependencies or retrofit requirements that you would have with the UVM test bench. And the method that I've captured here, and I'll walk you through, is relatively simple. This is not brain surgery by any means. It is relatively simple, but it is also something that I had not considered before, and it was very useful for me, and that's the reason why I considered sharing this as part of the conference. So the method here, it's 4 steps. First is you're looking at all of the software status outputs from your DUT, and you're mapping them to all of the relevant control registers or I/O. I'll show you what that looks like in a second. Second, bit by bit, you're looking to capture a checker strategy, and you want to see if formal is a feasible technology for verifying each of those status outputs. Then you're going to go away and do the work. You're building the actual properties to prove each of the status outputs, and then you summarize it with some simple but practical documentation that you can review with design engineers or the rest of your team. So let's walk through what this looks like. First of all, so step by step here, we're going to start by mapping a status register.status bit. This is the thing that we're proving. And we're going to map that back to all of the relevant control registers and top level I/O. So you can see this, status register.status bit is influenced by control register 0 some field, control register 1 other field, and some top dot and top dot any input. Next, just not the dependency on that, but now you want to look through and understand the relationship between the different control registers and top level I/O and the status bit. So this, more or less, you're visualizing a little model here for how those inputs feed into and relate and control the state of the status bit. So based on that, I have done this by just drawing crude little diagrams. This can be simple or very complicated, but it is important here, like I said, to just capture the relationship between the different control register and I/O and the status bit that you're focused on. With that, I've been able to capture just a general strategy in a table here. You capture the strategy, so you understand what you need to do here. You understand, the types of things that you are going to, or the way that you are going to build your properties. You identify the specific output that you're focused on. In this case, it is status register.status bit. And then for me, it was important to recognize any kind of limitations here. And the limitations were useful in that sometimes formal property checking for a specific status bit is actually not the right tool for the job. And so this is your chance with this type of high-level crude analysis and planning. This is your chance to identify feasibility. You either go forward with formal, or you interrupt and you find a different approach. Then the work starts, and this is just the mechanics of writing properties, based on the strategy you've got, based on the relationships that you have defined. You go and build, one or more properties that prove that particular status output. You run those properties, you make sure that the RTL is functioning as you expected. You do your job. This is the do your job step. Go and write code and make sure that your proofs are passing. And when all of that is done, or as you are doing it, I found it useful to document the properties that you have constructed, so that you can go through and review that documentation with the rest of your team, ideally with the design engineer that wrote the RTL. So again, here you're looking at the property, what is the name of the property, so you itemize the properties that you've constructed. Generally, you look at the when condition, so this is the situation that I am looking at, and when that happens, this is the thing that I'm going to be checking. So again, the when condition here is, some field and another field and input, something happens, and when that happens, I go and make sure that my status bit is asserted. It's important here to not just regurgitate or capture the property specifically. You want to write this in layperson's terms, so it's more of a summary of the property, or a summary of the check, not the guts of it. You want it to be something that you can review. This is not a code review. This is a review of intent, if you will. So, like I said, the 4 steps, it's not brain surgery, but these are the steps that I went through for this approach that I found to be, very useful. And the most useful part of this that I had actually never done before, was the actual mapping. So these are just snapshots of documentation that I made along the way of applying this formal property checking to software status. On the left is just a blurred out mapping of one particular bank of status outputs that I was looking at. So the status bits under test, if you will, they're in that gray box. All of the things connected to it are various control registers in my design under test, and some of those are I/O, but these are primarily control registers. So the way this started was, I just have the status bits in the middle, and one by one, I trace all of those back to all of the not just the control registers, but the actual bits, the fields in each control registers that influence that. So you end up with a big spider web of relationships. Again, that to me was really, really useful, because it's like a very low level mapping of what is effectively a low level verification technique to verify low level behavior. So again, it was a very practical exercise and useful outcome. On the right are 2 snapshots of documentation that I used to capture effort from 2 different blocks. So there's one there with a picture. Again, here you can see the strategy, the outputs, limitations, as I showed you. The strategy here you can see is relatively brief. It just describes, kind of roughly what and how you're going to do for that status output. Limitations captured here, which again I think are relatively important to validate feasibility. Some of these required a picture. This is my mess o logic there, just to describe the relationship between status bit and control register input and I/O. Sometimes that was necessary, sometimes it wasn't. And then in the picture behind there, you can see where I've itemized all of the different checkers for one particular status output. So there's 1, 2, 3, 4, 5, 6 different properties written. I have extra fields here for parameterization and configuration where appropriate, and just a general description of the when condition and the what I'm checking, and then any other notes. Again, the notes are more of a topic of discussion, and then this is the type of thing that I would go through specifically with the design engineer, but also members of the team, so everyone can understand what has happened. So that's kind of a snapshot of the application here. Again, kind of the least important part about this is the actual writing of the properties and the assertions. This is more about the application of it. So figuring out where to apply it and how to apply it, and not so much the details of how you write the code and how you write properties and whatnot. I think there's a lot of good resources for that, but not a lot of great ideas for where verification engineers who are friendly with simulation can actually reasonably get started here. Just some general results and observations. So just kind of the technical details here. This is an effort in progress, and at a snapshot from a few months ago, I had made my way through, I think, 15 different status outputs proven, and in so doing found 6 bugs with roughly 70 different properties written. And this was weeks, months of effort. So yeah, bugs found, that's always something that makes you feel pretty good about it. But in terms of gut feel, this felt like a very reasonable way to approach verifying software status, and it felt much more reasonable than overlaying on simulation infrastructure. Notably, there was no dependency on simulation infrastructure, so there was no effort put into pulling different simulation components or configuration or anything like that. This was completely independent, and it was completely reasonable to do that. In the mapping exercise, that big spider web of connecting status to the related control and I/O, that was a really useful exercise to visualize the low-level relationships. Again, this is like a low-level means of capturing those low-level relationships for low-level checks. So it just felt right doing that. The documentation that I captured, it was, I think, sparse but very practical for and it fit the purpose. And again, the working through checker strategies was good for recognizing that some software status that I wanted to verify with formal just wasn't appropriate. So it gave me a chance to recognize that and kind of cross that off the list of possibilities. Infrastructure or lack thereof was really neat for me. Again, coming at it from simulation where we're used to just building gobs of infrastructure. This is a low infrastructure route, formal property checking in general. I found it to be very low on infrastructure, which is really a really nice change. One thing that I did recognize was simple was good. Simple was better. I know that I've heard the recommendation of keeping properties simple. I've heard the recommendation of using helper logic, kind of logic outside the property to keep properties simple. I would go further than that to say try not to use helper logic as much as you can, because for me, the tendency to need helper logic meant that I was building properties or checkers that were getting to be a little bit too complicated, and it was a sign that I needed to simplify. So instead of a guideline that says keep your properties simple and use helper logic to keep them simple, I would have the recommendation of keep your checker simple, which means the property and helper logic are both minimal, or as minimal as possible. In terms of lessons learned, I've got a couple here. One that was really useful revolves around this idea of checker execution state. So, like checker execution state for me means you have to take your circuit to some state, and then at that state, you influence it in some way to make sure that it behaves correctly. So you have to get somewhere first, then you apply your check for the true or false outcome. Now, just to illustrate here, I've got the classic FIFO full, FIFO overflow example. So in simulation, this is a relatively simple thing to do. You would go through, you write a little test that would first fill the FIFO. That takes you to your checker execution state. Then you would write one more time and make sure that there's an overflow. So this is a procedural test. Again, you go through the process of filling the FIFO, then you exercise it with one more write, then you verify the overflow. So you can do the same thing in a formal property. You can write, some number of times to fill the FIFO, then you can apply one more write to ensure that there is an overflow. This is reasonable, and this is how I started writing properties when I went down this route. It's reasonable, but I felt like I made a major breakthrough when I quit thinking in terms of procedures to take the circuit to where I needed it to go, and instead just declaring where I needed it to go with by describing the checker execution state itself and not the procedure for getting there. So really, that state is making sure that the FIFO is full. And so with formal property checking, you don't have to tell it how to get there. You just have to say, take me there, or this is where my check starts. And at that point, you can just say, well, just take me to where my fill level is full. And from there, I will exercise it with an additional write, and I'll make sure that the FIFO overflows. Just by realizing this, again, with my simulation background, I think I was lulled into the idea that I needed to write properties similar to how I would write a procedural test. But with formal property checking, you don't need to do that. You can rely on the tool to take you to where you need to go. If you can describe the state that you need to be in, just describe that state, let the tool take you there, and then you apply your stimulus and check from there. So this was a really important lesson learned that let me significantly simplify the properties that I was writing. Another lesson learned, that first lesson learned with the checker execution state, I think that could be universally applicable, so I would recommend that regardless of what you're doing. This next one is more of a performance-related lesson learned, and this one may or may not be appropriate for you. But the design that I worked with had some large arithmetic functions. Just for an example, a large pipeline multiply that took several cycles to execute. When I started writing formal properties that relied that included RTL that relied on the pipeline multiplier, the properties took a very, very, very long time to prove, even if and sometimes they didn't prove at all, just because the size of the multiplier, so not even the depth of the multiplier, but also the width of the vector inputs, basically choked the tool. The tool couldn't handle it. So after some trial and error optimizations, I realized it was going to be better to sub out that pipeline multiply RTL function, swap that out, and swap in a much simpler RTL model, which is basically just an in, result equals in A times in B. That was much, much easier for the tool, for the formal tool to digest. Like I said, the real RTL sometimes didn't even finish very, very basic proofs, just because the solution space was so large. But with the much smaller RTL model, looking at execution time of seconds. So If you have logic, for me again, this was arithmetic functions, so they're easy to describe, maybe complicated on the implementation, but easy to describe. Those are opportunities for you to sub those large complex implementations out for smaller, faster models. Another thing that I did along this lines for performance was I found I changed parameterizations of specific models, of specific RTL module instances, again, to shorten pipelines or use narrower bit widths where possible. So again, just as a general comment here, if there are deep pipelines in your design, it's going to probably be worth looking at opportunities, whether it be modeling or through parameterization, to shorten those pipelines. If you have large arithmetic function, it might be easy to sub in just easy models. Now there's a few things that I didn't touch here that are still included in the paper if you're interested in reading more. One is a couple of pages just in general of simulation versus formal in verification thought leadership. I think as a community we have a lot of room to grow here. We've given simulation a lot of attention for many, many years. I think formal, while it isn't necessarily new technology, I think it is underused and undervalued, and there are opportunities here. So I get into that more in the paper. The specifics, I look at using Verilog configurations for binding and inserting faster models for performance. That's something that I look at and describe more in the paper. And then one thing that I also found quite important was a four-phase property checker template that I used that describes the structure of the properties that I wrote, which again I think is a fairly useful recommendation for other engineers that are getting into formal from simulation. But in summary, just generally speaking, again, coming back to the simulation versus formal, I don't think because is a real good look for us. Just because we've used simulation doesn't mean we need to continue using simulation in all cases. Rely on simulation for what it's good for, but for where it is not, constructive or effective or productive, we can be looking at down other avenues. So stepping out of our simulation ruts that we have worn into the job, and looking at formal as a potential alternative. If you are looking for a place to start, look at how you can use formal to complement what you already do in simulation. Module level checking, again, I think is the natural starting point, but I don't know that it's the best starting point. I saw software status and interrupt checking as a really practical complementary thing that we can do with simulation. But I think generally speaking, anywhere where low level checking is feasible, I think that maybe we can be stepping away from the big heavy UVM simulation, UVM test benches and simulation, and looking at a low level technique to proving low level functionality. Thanks a lot.